So hopefully you've had a chance to look at the application questions by yourself. I'll just go through them quickly now so that even if you got stuck, you've still done them. So for question 15, we're asked to use the Pythagorean identity sine squared x plus cosine squared x equals 1 to show that tan squared of x plus 1 is actually equal to 1 divided by cos squared of x. So the first thing that I should note is that you can't actually do that unless you also use the other identity that tan of theta is equal to sine of theta and cosine of theta. So we are asked first to so we're going to be showing that the left-hand side of the equation, which is tan squared of theta plus 1, equals the right-hand side of the equation, 1 over cos squared of theta. So the first change we should make is we need our answer in terms of cosine of theta, so we need to get rid of our tan of theta on the left-hand side. One way of doing that is to remember that tan of theta is equal to sine of theta on cosine of theta. So we just insert that value in for tan of theta. So remember that this square is squaring the whole thing. So we have sine of theta over cosine of theta squared plus 1. So from our index laws, we know that squaring a fraction, that square is distributive. So it squares the sine theta and it squares the cosine of theta. We still remember that we want only cosine of theta in our answer, so wise decision might be to convert this sine squared of theta. So that's when we use the rule that they asked us to use. So we know that sine squared of theta is cos squared of theta plus 1. So if we subtract we subtract cosine of theta from both sides, we end up with sine of theta squared equals 1 minus cosine of theta squared. So we can substitute sine squared of theta equals 1 minus cosine squared of theta in for this sine squared of theta here. So the top line becomes 1 minus cosine squared of theta. Next, we want to combine these two terms. So in order to do that, if we want to add two numbers, we need to have the same denominator. So just knowing that 1 is the same as cosine squared of theta on cosine squared of theta. Now we can add those two fractions, 1 minus cos squared of theta plus cos squared of theta over cos squared of theta. When we do that, we have a minus cos squared of theta and a plus cos squared of theta, and those two cancel out, and finally we're left with the desired right-hand side of the equation. So these type of questions are my favorite. They do take a little bit of fiddling around. The textbook does this question, or the solutions manual does this question in a different way. I spoke to Mrs. Charco about it, and neither of us really agreed that it did that in the right way, because it really should have shown that the left-hand side equals the right-hand side. I think in the actual textbook answers that are like at the end of the chapter, I think it did it this way, but in the solutions manual it does it a different way. So I would follow this method where you show that the left-hand side is equal to the right-hand side. So in part B of the question, we're asked to use the identity that we've just derived to evaluate what tan of x is, given that sine of x is 0.6157. Okay, so if sine of x is 0.6157, we need to first find out what cos squared of x is, and we can use our identity cos squared of x equals 1 minus sine squared of x. We need to find what cos squared of x is because the identity that we've derived calls for it. So squaring 0.6157 squared, 1 minus that number, you can do that on your CAS. You should find that that is, once you type that in, that is 0.6209. So now using our rule, we know that tan squared of x plus 1 is equal to 1 over cos squared of x. So just putting in the value that we just found for cos squared of x, and I shouldn't have a little. So dividing 1 divided by this answer that we just found. So when you do it on your CAS, instead of using the rounded up version of the number, go 1 divided by and then use the value that we calculated here. Now that avoids any losing any accuracies in our calculation. So that turns out to be 1.611. So next, we've just found out what tan squared of x plus 1 is equal to, so we need to find out what tan of x is. So our tan of x, if we rearrange this equation, subtracting 1 from the 1.611, and then finding the square root of both sides will give us tan of x. So again, I'm going to use the value that I calculated in the previous part of the question. I'm going to write that as the square root of that value. Oops. I'll do that again. Square root of that value minus 1. And we get that that's 0.7814. So question 16, I hope that you could do this by yourself. It's just taking us right back to SOHCAHTOA. So it's a tree diagram. We've got a tree of some height and a shadow cast of some length. So it's this right angle triangle. A reference angle is this pi on 3 here. So that's the hypotenuse, the opposite side, and the adjacent side. Oops. So we should be able to find the height of the tree because it's the opposite. So opposite and hypotenuse, that's sine equals opposite over hypotenuse, height over 30. Multiplying both sides by 30, we get the height is 30 times sine of pi on 3. We should recognize straight away sine of pi on 3 is a special angle and it's the square root of 3 on 2. So 30 times the square root of 3 on 2, 30 divided by 2 is just 15 square roots of 3. And do not forget your units. It's the application question, so we need to include them. Similarly, the shadow is this length here. It's the adjacent, so that's using the cosine. Cosine equals the adjacent over the hypotenuse. So if we multiply both sides by the hypotenuse is where I get this 30 cosine of pi on 3. Cosine of pi on 3 is a half. Half of 30 is 15 meters. So hopefully that one should have been an easy one. Next one. This is where physics overlaps with maths methods. So we've got the weight on a spring moves in such a way that the speed v centimeters per second is given by the rule v equals 12 plus 3 times sine of pi t on 3. So we're asked first to find the initial speed. As soon as you see the word initial, that implies that time is equal to 0 at that point. So we want to make a substitution. We want to let t equals 0 in this equation. So letting t equal 0, we have 12 plus 3 sine of 0 because that whole thing goes to 0. Sine of 0, special angle sine of 0 is 0. 0 times 3 is 0. So we're just left with the velocity, or the speed, 12 centimeters per second. Next part of the question, we need to find the exact value when the exact value of the speed of the weight after 5 seconds, and then C, the speed of the weight after 12 seconds. So there we're just making substitutions, t equals 5 and t equals 12. If we make the substitution t equals 5, we get sine of 5 pi on 3. So sketching that, 5/3, 1/3, 2/3, 3/3, 4/3, 5/3 puts us in the fourth quadrant. Sine in the fourth quadrant is negative, so this becomes negative 3 sine pi on 3. Pi on 3 is the reference angle here. Sine of pi on 3 is exact angle square root of 3 on 2, so we're doing 12 minus 3 times the square root of 3 on 2, and we can just leave that answer as is. And don't forget to put your units centimeters per second. And we will put 12 in there. 12 pi on 3, 12 divided by 3 and gives us 4. Sine of 4 pi on 3, we could draw that. 2 pi, 4 pi, it would just be right along the x-axis. Sine, being the y-coordinate, has a value of 0. So 3 times 0 is just 12, leaves us just with the 12 again, so 12 centimeters per second. 18 can be completed in a similar way to question 17.